Well, hello and welcome to the 39th lecture of this short course called Behavioral Theory of Systems with a view towards data driven control. We were in the middle of data driven simulation. Let me remind you what we were looking at. We have measured data given by u0 hat, y0 hat, u1 hat, y1 hat, dot 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 up to ut hat and yt hat. Yeah. From this measured data, is it possible this is measured data? Is it possible to know what u and y are on this timeline for some L much smaller than capital T, of course? Is it possible to find this out from here? Yeah, that is the question of data driven simulation. What we did was we assumed assume that the input u hat is persistently exciting of order n plus L plus 1. If it is of order n plus L plus 1, then we have shown that this implies this matrix u 0 L T minus L x 0 T minus L, this matrix rank of this matrix is equal to L plus 1 times m plus n. In other words, this is full row rank. Okay. That is what we have established in the last lecture, and this follows from actually fundamental lemma, follows from fundamental lemma. Okay. Now, now you see so right. So, how do you what is the expression for this guy? Let us write an expression for this guy, and so from there perhaps we will be able to derive something. Yeah. Let us see what is u0 y0 u1. Let me write first few of them, u1, then we will be able to understand what is going on. y1 u2 y2, this should be enough. I think I want an expression for these guys, right. Okay. So, this is equal to, in fact, what is u0? So, let me write down first the independent variables which give us these guys in general. What is independent? Of course, the initial condition state is independent, yeah, and the inputs are independent. So, u0, u1 and u2, in this case these guys are linearly, and these guys are my independent variables, can be chosen freely. Yeah. Now, if I want to relate u0 with this vector, it will be, so if I write down it is a matrix vector multiplication thing. So, going to be x0 u0 u1 u2. So, this column, the first column gets multiplied by x0, second gets by u0, third u1, fourth u2, and I want u0. So, this will be its identity of size m 0 0 0, great. No, what will be y0? No, look at y0 from my state space equation. Y0, let me go way back, where is it? Yeah, y0 is given by cx0 plus du0. So, I put that guy here, c times x0 plus d times u0. Remember, we have actually looked at this matrix before also, but I am just refreshing your memory. What is u1? 0 0, identity of size m 0. What is y1? y1 is equal to c times x1 plus d times u1, but x1 is not with us, right. So, d times u1 will be there, but I will use for x1 I will use ax0 plus b u 0, which will give me C A times x 0 and C B times u 0, right. What is u 2? 0 0 0 identity of size m, and once again following the same trick, I will have this guy as C A squared, I will have this guy as C A B, this will be C B, and this will be D again. Remember, we had used this matrix to do the rank calculation, right, to do the dimension calculation of those B L's. This is the matrix, but now I am going to rearrange these guys a little bit. How do I do this rearrangement? Well, I am going to do the following. I am going to first do a rearrangement of the rows here, yeah, because I want this to be like this. I want this to be u 0, u 1 and u 2, and then y 0, y 1, y 2, like this, okay, which I will call in short. I have a shorthand notation for this. I will call this as u 0 to 2 and y 0 to 2. That is the shorthand for this vector. So, this vector after this rearrangement would be the following. I also want a rearrangement of the columns, because I want this to be arranged as u 0, u 1, u 2 and then x 0, okay, right. So, now let me put down this matrix here. First column obviously corresponds to u 0, u 1, sorry, I am writing them a little too close to each other, u 0, u 1, u 2 and x 0. Okay. Now, notice this will be just identity m 0 0 0 identity m 0 0 0 identity m, that takes care of the u 0 to 2 part, u part. What about the x part? Okay, x does not show up here at all. Now, y 0, y 1, y 2, they depend on u 0, u 1, u 2, this first 3 guys. How? They depend through this matrix, is not it, right. And what is that matrix? Sorry, not this matrix exactly, sorry, my bad. It depends on okay, this matrix, then this matrix and then this matrix, right. So, they will come out to be D 0 0, C B D 0, C A B C B D, like this, and this guy will be C C A C A squared, okay. Yeah, look at the pattern. Yeah, this looks really nice. Let me rewrite this guy for you. What we have shown here is that u 0 to 2, well, let me write for 2 first and then we will write the general case. This is equal to identity of size m times, so 3 times m here, 3 times m block 0. This is the observability matrix of order 2, because I go up to a squared, right, order 2 is observability matrix, and here what I have is a Toeplitz matrix created out of D and C and A and P, like this is a Toeplitz matrix. You see this, because the diagonal is the same, this off diagonal is the same, this off diagonals are the same, yeah, like that. So, it is called a Toeplitz matrix. The name of this, it is a Toeplitz matrix, Toeplitz matrix, yeah. So, that is why T. What is the size? Size, once again we will use the letter 2 here, okay. This multiplying what? This multiplying u 0 comma 2 and x 0, okay. That is what we get out of this guy, all right. Now, in general what we will have is u 0 to L and y 0 to L, this vector an arbitrary vector. An arbitrary vector will be given by I L plus 1 times m, 0 here, Toeplitz matrix of size of L, yeah, and observability matrix of L. This multiplying this vector, and this vector must be an arbitrary vector. So, what should I write for that arbitrary vector? Let me write A. Yeah. So, if I want data driven simulation, I just need to know this matrix, and I need to know this A of size are L plus 1 times m, right. Yeah, that is the size here, L plus 1 times m, that many input is what we have, is not it. See, this is a vector of size m, m, m. So, L plus 1 times m plus n, because this is this x 0 is arbitrary. So, if I knew this matrix, if this matrix is known, then I can do simulation, I can get all these trajectories. This is just a rewriting of your state equations in a form which is like a parameterization in terms of arbitrary vectors. So, in fact, all I am saying is that B L is equal to image of this matrix, and trust me, we have seen this before when we were calculating the dimension of this vector space. In fact, we calculated the rank of this matrix, but that is not the point. The point is that this simulation is impossible in general without doing the identification, because this requires us to know what the system parameters are, system matrices are. You see, this entire matrix is created out of, these are identities, that is not a problem, but for this Toeplitz matrix and this observability matrix, you need to know what C A B are, C A B D, A B C D. So, to know this and to know this, you need to know A B C D matrices. Can we skip that? Is it possible to skip it? Yeah. Notice that I have A here, right. This A is an arbitrary vector of this size, but now notice what had we assumed, persistency of excitation, and that had told us if the signal is persistently exciting of order n plus L plus 1, then this matrix is full row rank. That means this matrix, the image of this matrix is full u 0 L t minus L x 0 t minus L. This image is full. What does that mean? This means this is exactly equal to the vector space, the Euclidean vector space. It is the image of this matrix is the Euclidean vector space of dimension exactly equal to the number of rows here. What are the number of rows here? L plus 1 times m plus n. Wow. So, that means any vector here can be written as a linear combination of the columns of these guys, which means in particular for this A is also this size, right. So, for this A, for all A in R L plus 1 times m plus n, there exists a V in R. What is the size of this matrix? What is the number of columns here? The number of columns here is exactly t minus L plus 1, t minus L plus 1, such that A is equal to u 0 L t minus L x 0 t minus L times V. So, I plug that in here. We have u 0 to L, y 0 to L, that is equal to identity L plus 1 times m 0 Toeplitz matrix L observability matrix L multiplying u 0 L t minus L x 0 t minus L acting on V. But now notice what is this guy, what is this product? You can immediately see that this product, because of its very structure, this product is as follows. This product is, of course, the top guy will be u 0 L t minus L only, because of this identity matrix sitting over here. Yeah, yeah. This product is just this. What is this product? This product is T L acting on this and O L acting on this. Just verify that this is nothing but y 0 L t minus L, that is the Hankel matrix created out of y. and that acting on V. Now it is so interesting, it is so fantastic. Why? Because what have we achieved? We have achieved that u 0 L and y 0 L for an arbitrary trajectory in fact is a linear combination of this V. Yeah. So, and because because this so for every trajectory here there exists a V such that you have this, and whenever you pick a V, you just, because it is of this structure, it follows that it is going to be in fact a trajectory like this. It will satisfy the given state space equations. So, in fact we have a parameterization. Yeah, this is the parameterization and this is the data driven simulation. Data driven simulation is done. Perfect, no? Yeah, see the beauty here, I do not need ABCD matrices, I do not need to know ABCD matrices, just assume that the input is persistently exciting of order L plus n plus 1 and then construct this matrix from the data, that means create the Hankel matrix essentially, and then every trajectory restricted to 0 to L timeline is actually given by a linear combination of the columns of these guys. Yeah. In fact, we have not said anything new, it is just a restatement of what we have seen. This is the Hankel matrix of size of order L created from the data, and all we are saying is that BL, the behavior restricted to 0 to L timeline, is in fact given by the column span of the Hankel matrix, that is what it is. But we have stated it in a different manner using the state variable and so on. So, therefore, from now on, instead of saying persistently exciting of order n plus L plus 1 all the time, what we will do instead is we are going to assume that this matrix U 0 L t minus L x 0 t minus L, this matrix is full row rank, that will be our standing assumption. Yeah. We will keep on playing with these numbers though, this number L in particular to say various things, right, which brings us to the next point of data driven analysis. What we do for data driven analysis, in particular we will see this case when L is assumed to be 0, right. So, we assume that U 0 t and x 0 t, this matrix is full row rank. What does that mean? That means the rank of this matrix U 0 t x 0 t, what is the rank of this matrix? We are assuming that the rank of this matrix is equal to the number of rows here. How many rows are here? There are exactly m number of rows, here exactly n number of rows. So, I am assuming that the rank of this guy is m plus n. Yeah, that can be guaranteed by assuming that the input is persistently exciting of order n plus 1. Yeah, just think about it, n plus 1, that is why this rank is equal to m plus n. For data driven analysis, what we will assume is that suppose this data is available to us, if this data is available, we are asking this question, is the system stable? Yeah, you see, this is one example of data driven analysis. Is this data, is the system that is generating this data, is this system open loop stable? I say open loop because that means that when the input is 0, this is open loop stable. How do you even answer that? Think about this, I have a finite time series data and stability is something that goes, it requires you to find out what happens to the state trajectories if there are 0 input, but non-zero initial conditions. Is it true that for arbitrary initial conditions the trajectory that you get that dies down to 0 as t goes to infinity. Yeah, that is the idea of stability, asymptotic stability. Is this open loop system asymptotically stable? How do you even know that? One way to do it is, of course, you identify the system. Yeah, you identify the state matrix A, and from there you find out whether that A is sure or not. That means you find out the eigenvalues of A. The eigenvalues are within the unit disk, then it is guaranteed to be stable. Okay, it is asymptotically stable. But how do we do this? How do we find this out? How do we find out A from here? A from the data. In fact, it is not very difficult. You see, all I need is one step more information. I define x1t to be equal to x1 x2 dot 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 up to xt plus 1. Earlier it was x0 up to xt. It is worthwhile to write it here so that we do not forget x0 x2 0 x1 dot 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 up to xt, and now I start from x1 and go up to t plus 1. If there were, if xk plus 1 is equal to axk plus buk, then notice that you can write this thing immediately. x1t, this matrix, must be equal to b a matrix multiplying u0 t x0 t. Yeah, just do a quick verification. It immediately follows from this recursive relation that the matrix wise they must satisfy this condition. The only unfortunate part is that this is unknown. We do not know this from the data immediately. This is unknown. So, what can we do in this situation? This is unknown. All I know is that this matrix is full row rank. What can we do for that? So, when I know that this is full row rank, I can immediately do the following. I can find out its right inverse. If a matrix is full row rank, you can find out its right inverse. U0 t x0 t. For it to be a full row rank, you see it has to be a fat matrix in general. It cannot be tall. If it is tall, then guaranteed not full row rank. It has to be fat or square at most, not more than that, not more number of rows than that. So, that tells us that this what is this size? This is n, this is n plus m, sorry, m plus n here. So, t plus 1 must be bigger than or equal to n plus m. So, that means we have sorry, that is not here. We actually need a little more. We actually need a little more information, but that is okay, because of persistency of excitation. But in any case, so persistency of excitation would require that this u 0 I want it to be of order n, right. So, n t minus n, that must be full row rank. Yeah, this is for persistency of excitation idea. This must be full row rank, but that will require what? That will require how many rows does this guy have? This has n plus 1 times m, these many rows. And how many columns does it have? It has t minus n number of t minus n plus 1 number of columns, isn't it? So, all I need is that this must be true in order for this to be full row rank. So, therefore, t must be bigger than or equal to n plus 1 times m plus n minus 1, like that. Okay. That is the bound on this number t, but if that is true, then obviously t is bigger than m, right. T is bigger than or equal to m. So, this matrix being full row rank is not a problem when we assume this is persistently exciting. So, that the t is not a problem at all. So, this is full row rank, right. Now, what was I saying? So, I have a fat matrix, okay, x0 t, a fat matrix I have. All what I do is I multiply this guy from the right by this product, I multiply by this transpose. Because it is full row rank, this is going to be full column rank. When the product is there, product is of smaller size exactly equal to the number of rows here. So, here it is n plus m. So, this matrix n plus m has rank exactly equal to n plus m, which is a square matrix of full rank. So, this is invertible n plus m by n plus m. This can be multiplied by from the left by u 0 transpose sorry u 0 t x 0 t transpose, right. This has how many rows? This has exactly t minus t plus 1 number of rows, and it has n plus m number of columns. Okay, n plus m number of columns. Yeah. And see, I just checked that this condition which I need for persistency of excitation. This also means that as a result, t is bigger than or equal to n plus m, which is good because that means these matrices are also fat matrices. Okay. So, I have this guy, and this is special. This matrix is called u 0 t x 0 t. Its right pseudo inverse, or right Moore-Penrose inverse. When a matrix is full row rank, there are multiple right pseudo inverses, multiple right inverses, but this guy is special, yeah, because this guy has certain properties, as we will see soon. So, what we will do is, remember what we have x 1 t is equal to b a u 0 t x 0 t, and this matrix is full row rank. So, I multiply from the right on both sides by its right pseudo inverse, that is this plus u 0 t x 0 t right pseudo inverse. Okay. If I have a right pseudo inverse, notice that when I multiply from the right, this becomes identity. Yeah. So, in that case, we have B A given by x 1 t multiplied from the right by the right pseudo inverse of this matrix created from the data. That is my B A. Okay. Now, once I have that as my B A, so from there I can just read off B A, yeah, and I have identified the system, okay, right. So, this is identification, and there is no wonder that I am able to identify this, because I have assumed that the system is persistently exciting of order n plus 1, yeah, and because it is a first order system, its lag also is n. So, n plus 1 in this case L is equal to 0. So, therefore, we are beyond the saturation point anyway in this case. Because we are beyond the saturation point, it is possible for us to identify the system. So, that is why we have been able to identify this B A. One important point to note here is that if I use the pseudo inverse, you see when I do this, I am assuming that this actually was true. I am assuming that this was an equality, but in general when you are collecting data and suppose there is noise, or suppose there is noise, in that case this equation will not be satisfiable. I do not know this B A, but the measurements that I have done for this, the measurements that I have done for this and this, it may not always be the case that x 1 t is in the row span of this matrix. It is full row rank. So, its image that is column span is full, its row span is not full. Full row rank does not mean its row span is full. Like for example, I have this matrix 1 1 1, this full row rank, but what is its image? Row span. Row span is a subspace of R 1 cross 3, dimension is 3, right. This row span has dimension equal to 1. So, it is not full. So, therefore, here also it may so happen that this guy this because this row span is not full, the data that I have about x 1 t may not be such that x 1 t is in the row span of this matrix. In that case, what will happen? In that case also, if you do this blindly x 1 t and u 0 t x 0 t dagger right inverse, what do you get? You in fact get this answer. This in fact is equal to, I should not write it by definition, this is in fact equal to the minimizer of this quantity x 1 t minus b a multiplying u 0 t x 0 t, this the Frobenius norm of this guy over all possible b a's. So, when I do this calculation, I actually find out this you can find out from any matrix computation textbook. We do not have time to go through this, but this is pretty standard. So, when you have an equation A x equal to b and b is not in the image of A, the best thing that you can do is multiply by the left inverse of this guy, provided this A is full column rank. Yeah, it is just the transpose of this situation. Yeah, and to find out this the best possible guy, the closest possible guy, a closest possible B A that makes this product closest to this x 1 t is this guy, right. So, that is why even when your data is such that it is not identifiable, but still you can get not identifiable in the sense that if the data is such that it is corrupted by noise or something. So, x 1 t is not in the row span of u 0 t x 0 t, you can still find out the underlying B A or at least an approximation of that by doing this right inverse business. And once you have that right inverse, you have you can find out what this A is. Yeah, and if you can find out this A, then from there you can find out the eigenvalues of A and figure out whether tells us about open loop stability, right. So, I think I have run out of time for today's for this lecture. What remains is to do this data driven control. Yeah, we have done data driven simulation, we have done data driven analysis, where all that remains is a discussion on data driven control, and that we will see in the next lecture. Yeah, till then take care of yourselves, bye.